Because if I put the mic on and then I cough, then it's just amplified. So I will let you know not.
Okay, so just so that everybody knows, there's a traffic jam. Because of that, the sentence cannot be yet, so we will have the next session now before the last start. We'll give you food for thought. So today he will talk about context-dependent selectivity and two natural scenes in the retina.
Yes, that's right. Yes, at first I was actually kind of afraid that the topic of my talk might be a bit orthogonal to what this workshop, which was about. By the way, thanks for inviting me. It has been a very interesting night workshop, and I hope you're not going to regret not being fed for my talk. But at the end of the day, actually, watching several talks, I felt like there might be some interesting connections. So let's hope that you can enjoy it, because I'm kind of starting from a very different point of view, and then maybe coming back to some of the points that were expressed in this in the previous talk. Anyway, so okay, I'm gonna start with like a very broad point here, which is about normal coding in sensory systems. So classically, what we want to understand, and I think we've seen this in our picture before, is you have a stimulus, so ideally you would like to understand what happens during natural stimuli. So you have natural stimuli, and you record it from your favorite area of the brain, so you get neurons here, each line is a different neuron here, and you would like to understand the relation between this natural stimulus and the cells, and that's a very complicated task, but it's a task that people have tried to do for many decades. And so just to be a bit of, try to classify things. I'd say, broadly speaking, there's been two categories, or at least two extremes, in terms of how people try to address this issue. The first one is to actually use artificial stimuli, like for example white noise or grating in different orientations. And for example, if you just show that and record some neurons in V1, my second favorite area, you can actually get receptive fields or tuning curves, or artificial tuning curve. And like some people actually dismiss these things because these are artificial stimuli. If you do, you're totally entitled to it, it's fine. I encourage you to read that review if you haven't done it yet, because it's actually, you can disagree with what's in it. I don't necessarily buy everything they're saying, but I think it's a very nicely laid out argument in praise of artifice, as they say. And on the other hand, I would say the other extreme is to say that no, you actually want to use natural stimuli, show that and record some neurons. Like a modern version of that is actually then trying to learn some machine learning model like this one. This is taken from the review by Dennis and Ricardo, to try to predict the response of neurons based on these natural stimuli. But I just wanted to remind that actually this is not a novel idea per se. I mean, already Jerry Levin, there's a famous paper in the Retina where they were doing this. This is actually Jerry Levin doing experiment in his rig while smoking a cigarette, which, just to remind you all, the 60s were actually a really cool era. I see some people nodding there. Anyway, and there's been actually some back and forth between using natural stimuli and not using them and using artificial stimuli instead, at least in the retina field, and I think that's actually interesting to try to understand why people went back and forth. Anyway, so point here, that thinking about these two extremes, of course, several people have been trying to explore some possibility of a middle ground, and that's exactly what I'm going to talk about. So can we find a middle ground, something between these two approaches? Because the issue there is that, of course, you can do that. You can learn a machine learning model. But I mean, there's a question of like, people usually end up with some sort of anxiety syndrome of like saying, but what does that mean? How do we interpret that? Well, how do we know what these neurons are really doing? And I'm not going to dive into that debate, but that's the reason why you might find also limiting. So can you find a middle ground? And so I'm going to talk about, I'm going to address this question at the level of the retina, which is, I guess, all you know here. It's a thin piece of tissue at the back of your eye. We can record many neurons, and we can just try to answer that question there. And not going to say a lot about experiment technique here, but just to tell you a bit about it. The classical things we do in the lab is that, so this is the retina memory. So we start with photoreceptors that are transition light into electrical activity. Then it goes down to several layers. It's a complicated network. It's more complicated than what I'm showing here. And then at the end of the day, you have the ganglion cells that are sending their spike to the brain. And so here we take the eye out, sacrifice the evil, take the eye out, take the retina out, flatten it against an array of electrons. And so here actually you can see in yellow the electrodes and in green the soma of the recorded ganglion cells. This is extracellular recording, and out of that is nice spike sorting tools. You can actually extract, like here, for example, hundreds of cells, 200 of cells responding to any stimulus you want. And you can do that for hours. Actually, for the record, last time I went to Edinburgh was exactly in that room in 2019 for a spike sorting workshop. Good memories. So now, okay, you can recall all these neurons. So how do you characterize what these neurons care about? What do they do? What feature they extract from the natural scene? You name it. Classical way to do that is to, so let's say you have one ganglion cell here, and you're going to present many of these random checkable light patterns like this. And I will simplify things a bit, but I assume that for most of you it's actually bread and butter. And you're going to get responses for, let's say, each of these frames. I'm going to put the time axis under the carpet for most of the talk, actually. So you get your response to this frame, to that frame, to that frame. And then, classically, what you can do is a weighted average of all these frames by the number of spikes evoked. And if you do that, you obtain what people, a receptive field, which is essentially what people call the spike trigger average here. So here, in that case, this tells you that what actually evokes spikes is to have an increase of luminance in this area. Okay? I assume this is something everybody's more or less familiar with. If you're not, please interrupt me. I guess most of you are. So here you're happy, you found that there's a selectivity to local light increase, and you can make a slightly more elaborate version of that, but that's the same spirit because it's all starts with a filter, then you add some sort of fancy, simple nonlinearity here. But since Christina has already done some more elaborate version of that yesterday, I'm not going to spend time on this. So you can actually plug this filter that you estimate on the GLM and try to actually estimate and predict how it's going to respond to various stimuli. An interesting point here that is made by Lab, I took an example from Chichonis Lab, actually many people have done that, is that, so let's say you actually try to predict the white noise that you use to actually estimate this filter. It works reasonably well, right? So here it is basically, here each line is not a different neuron, here each line is a repeat of the same stimulus over and over again. So you see that you have reliable events here. And you see that the model can most of the time catch them. I mean, these two things are almost indistinguishable. So the model does a pretty good job at predicting the response of that single neuron. So everything would be great if it was always the case. The problem is actually if you now take the same model and try to predict the response to natural scenes here, it's a disaster. It really doesn't work at all. So there's more than just, the simple spike trigger average I was talking about earlier. These models just are not enough, even at the level of the retina. So if they are not good at the level of the retina, I can only imagine how bad they can be in other sensory areas. And it's been going on for a long time. And so we started from this well-known fact. We were wondering, okay, so how can we probe selectivity during natural stimulation, right? So if you start from your white noise stimulus, I mean, it's a great thing. You can build a great model that really works, but it really does not generalize for natural scenes. So you can actually just go directly and ask natural scenes, during natural scene stimulation, what ganglion cells care about, what feature they extract. And so we went back to this receptive field and thought about it and kind of decided to take them seriously. So the idea of this receptive field that I was saying earlier is that if you want, the best way to increase fine rate, the response of the neuron, is to actually increase light in this area, because it's a nonsense, you want to increase light in this area. So if you really believe it, if you really take it seriously, in a natural image, that means that if you have, if you flash this natural image, and you have your neuron responding to this natural image, now, what you should what you should do, if this is really what all the neuron cares about, is to, if you really want to increase the fine rate, the best way should be to actually increase light in this area, right? So just saying something very trivial here, you'll see why in a moment. But the idea here is that if this is really what you always care about, even in a natural context, then basically the best way to increase the fine rate should be to increase light inside the receptive field center. So that's actually something we can test. It's probably Stroman, but we can at least test it. So here's the experiment we did. So we start with this natural image, so it's which I'm going to call the reference image. And then we add to this image a checkerboard pattern. But one thing to say here, which is important, is that the amplitude of the checkerboard is relatively small. Basically, we choose it so that it evokes barely detectable change in the response of the neuron we're looking at. And that's an important point. So let's say it's just a small amplitude checkerboard. So that's what it looks like. So amplify a bit the checkerboard so that you see it better, but that's basically. So we start from the reference image and we obtain a perturbed image here. And then in the experiment we're doing, we do that for many different perturbations, always for the same stimulus, reference image. So you have this many different versions of the same perturbed image. And now we record the response of one neuron, or actually many neurons, so let's say here one neuron, to these perturbed images, and we see that some perturbations are better than others at increasing the fine rate of these ganglion cells. And so you can actually do the same thing we were doing before, right? You can actually just compute, basically do a weighted average of the frame weighted by the number of spikes emitted. And then you obtain a sort of a spike trigger average. Except that now the spike trigger average is always a perturbation around the image we started from. So we actually call it a local spike trigger average, because basically in the space of possible stimuli, what you're doing is that you start from a point, which is a natural image, and you just poke slightly in different directions. And you see basically what is the best direction in which you should go to increase the fine rate. That's basically what you end up with. Okay. So that's the basic idea. One thing to say here is that, which get people confused often, so I want to really emphasize it, is that in reality, we don't do exactly that experiment. We interleave this experiment by flashing, we interleave between this presentation of different perturbed images, other natural images, perturbed or unperturbed, so that there is no specific adaptation to these particular natural images. So this is not an adaptation experiment. This is not an adaptation experiment. We'll always get confusion, so I want to make it clear. It's really just probing, okay, what does it care about for that specific natural image? Okay? And so in fact, we actually interleave it with other natural images and also other perturbed natural images. So we get to measure this local STA, or receptive field, image-dependent receptive field here, for several images at the same time. Okay? So no adaptation here. Not saying that this wouldn't be an interesting question, but that's not what we're doing. So let's see what it looks like. These are just two textbook cells. One from this, well, that's actually axonal retina. It's close to a salamander, if you wonder. That's an off cell. This is basically the spatial receptive field. This actually is the temporal profile of the, basically it's a biphasic off cell here. And this is an on ganglion cell in the mouse retina. They're relatively textbook. There's nothing special about it, and I'm not cherry picking them. What I'm going to show you is actually something we see for many cells. So in the first place, actually, everything looks normal. So you can actually start from the reference image, which is actually gray, or you can start from the natural image. And, well, so every time you compute the local ST, as I was explaining earlier, and well, it doesn't seem to change that much. This ellipse is basically fitted on the, the classical receptive field estimated here. And I just put it everywhere here just for being able to compare everything. So actually, if you measure it based on the gray image, the difference between this one and this one is small, although it's not the same stimulus, right? Because here it's a high amplitude checkerboard, here it's a small amplitude checkerboard. But it's relatively similar. From here, from this natural image, it's actually almost the same, although you always see there's some displacement here, but not that much. And from mouse, it's more or less the same story here. So far, so good. So this is all the same cells again, right? But now, still the same cells, but actually starting from other reference image. It's the same experiment, same ganglion cell. Everything is interleaved. But now, starting from different natural images, well, we see something very different. These off cells suddenly prefer increase of light in this area, and this one actually prefer decrease of light in this area. That's more surprising, let's say. You also see that there can be, and we have quantified this, I'm not going to expand on it, but you also see displacement of the receptive field, of the locality. It's not always in the same place, and some of these displacement can be quite dramatic, but I'm not going to talk too much about it. Let's just say that they exist. Okay, for the retina aficionado, or for people who have somewhat heard about the retina before, you might say, well, actually, I've heard about these, I mean, you're talking about on cells and off cells, I've heard about these on-off cells. Are these guys just on-off cells? The answer is no. So, I mean, I'm not going to explain the details of that slide, but basically, these are all the type of cells where we see that effect. And sure, some of them are on-off, but many of them aren't. Happy to expand on that further if you're a retina aficionado. If you're not, just remember, it's just not just what people sometimes call on-off cells. So, okay, first conclusion from that work is that what we usually call polarity, the on-off nature of the cell, is actually depending on context. So usually people like to think that this might be carved in the stone. In fact, it's actually completely dependent on basically, which natural image, literally which natural image you're looking at. Okay. So that's kind of puzzling. And when you have something puzzling, you wonder, well, can we find a model to produce this finding? And there actually, what I'd like to try to convey to you is that there's actually something very theoretical about this. If you want, what we're doing is that, as I said, we start from a point in the stimulus space, we poke in many different directions, and we find kind of the filter that explains the best what happens locally. So basically what we're doing is a sort of if you think about the function that goes from the stimulus to the response of the ganglion cells, what we're doing is trying to find the best linear approximation locally around the neighborhood of that image that explains the response. And in other words, if you're familiar with that, that's basically this actually can be somewhat compared to the gradient of the stimulus response function. Except that here, we're actually estimating this gradient empirically in a relatively model-free way. Anyway, back to my question, can we find a model that produces this finding? So in the same experiment, we also interleave other images, like thousands of them, and also flashed, and that are interleaved with the perturbed ones, and that are different from the perturbed ones. And so basically, we're going to use these data sets to train the model. So basically, we have a set of images with no perturbation that are presented to the retina. We use that to train the model, and then we're going to just ask that model to predict the response to the perturbed images and possibly the local estimate. And we tried two types of models. The first one is like the null model of the retina, which is an NN model, so that's basically linear filter plus nonlinearity. It's very standard. I assume most of you know what this looks like, but basically it's a filter plus nonlinearity to avoid negative fine rate. And that's basically the null model of the retina. Then we actually wanted to be a bit fancier. And so when you want to be fancy in vision these days, you actually need to use convolutional neural network model. There's another reason, that's not just because of that joke. The other reason is that, as I say, this local estimate can be thought about as gradient. And if you remember your math courses, or if you are working on that, the gradient of the linear function is constant. So if we see changes, it means that there's something nonlinear going on there. And of course, if we want to model something nonlinear, actually maybe CNN is actually not a bad choice, especially in the retina. So I'm not going to spend too much detail on that. I'm happy to expand later on. First thing is that first we can actually ask. So we also have like different images from the training set that are not perturbed but repeated many times. And we can ask on these images how well the model is doing. And the answer is actually, well, the CNN model does better than the NN model, which is not such a big surprise. But the real question we want to know is back to this picture that you saw before, is whether we are able to predict the local STA. And, well, remember the theory, the constant gradient thing? Well, that's what you see here, right? So basically, the LN model is quasi-linear, and for that reason, the gradient is more or less constant, and for that reason you cannot predict. You can only predict a local STA which would be constant, which is obviously not what you see experimentally. Right? Maybe a bit of a strawman, but it's always good to actually check that. One thing to mention here, because I got that question before, again, that might be a very retina aficionado question. Some people told me, yeah, but if you actually have a linear filter plus a quadratic nonlinearity, like x squared kind of thing, could you actually reproduce things? Short answer is yes, you can actually predict polarity inversion, but what you cannot predict is actually displacement of the receptor field. And we do see displacement of these local STAs, so I don't think that's the good model for it. Which, by the way, tells you that the nice thing about these local STA measurement is that qualitatively they can already tell you to exclude some models just by the very nature of what you see there, without even learning models. Okay, and CNN can do everything to some extent, and so indeed, in our case, we could find a CNN model that actually could predict reasonably well these local STA, not just their polarity, but also sometimes their changing positions. It's not perfect, but it's good enough, let's say. One thing to say here, I don't have slides on it, but I think this is actually worth mentioning, is that in the process of finding CNNs, of course, as everybody, we are changing architecture, we are changing hyperparameters, we are changing many things. Sometimes you find, like, let's say, two choices of architecture and hyperparameters that give you the same performance for this measurement. So basically, they give you the same performance to predict how well, to predict the average response to some natural images. And then you take these two models and you ask them to solve that task, and one of them succeeds and the other one fails miserably. I think that's actually an interesting point to make here. Although I don't have, it's not something we have substantiated with a lot of trials and systematic study, but I think it's actually interesting to notice that in fact, because you're basically asking your model to predict the function, the gradient of your function, this actually makes the task harder, and it's actually a bigger constraint on the model. So did you have a question, or I see two hands? No, okay, so you have a question. Yes.
It's quick. How do you find the cells in the CNN? Are they
What I find the cells in CNN?
Yeah, they are single units in the CNN.
I'm literally, I have several layers, and I'm asking the CNN that the last layer predicts, basically the last layer is all so basically everything is convolutional up to the last layer, and the last layer, I'm actually literally asking them to reproduce the data. This is my objective function.
But
maybe I got you.
The cells, like the ganglion cells, receive input right away, so they don't.
Yes? No, they don't receive input right away from the natural images. There are several layers in the retinal circuit.
Okay. So you're trying to so those layers are trying to model the CNN.
Yes, I mean, you can take the CNN as actually just a model of the entire retinal circuit, which is composed of several layers. And one thing I'm not going to talk about because this is too much retina specific, is that actually we then try to simplify as much as possible the CNN model and try to map its component to specific cell type inside the retinal circuit. And we could actually find a different, and then generated hypotheses and then check them with additional experiment. And actually we could find some really relatively nice mapping. I'm not going to talk about that because I don't think it's necessarily suited for that audience, but if you want to hear more about it, I'm happy to talk about it later on. Anyway, so we're happy. We have a CNN model that predicts this finding, and long story short, on the mechanistic side, you need to basically have a convergence of the on and off pathway inside the retinal circuit to make it happen. So polarity is context dependent, and you have a CNN model that can replicate it. Now, you could end up there. But the problem is, this is actually where a lot of talks about, how things depend on, how sensory processing depends on context sometimes end up with. And I think they should not. Because how can the brain make sense of the retinal output with all these things? If it's literally changing its selectivity every time you show a different natural image, it's going to be hard. So, this brings me to the last part, Which is that then, since we have the model, since we have both the data and the model, we were wondering, so what's the relation between on one end the reference image and on the other end the corresponding local STA? Can we actually just explore, can we find anything systematic here? So just to go back to where we started, so, as I said, you can just imagine that you have several images and your neuron is responding to these several images. And basically, initially I told you, okay, so if your answer it only cares about, light increase inside of this area, then basically the best way to increase the fine rate should always be to just add this picture to that picture, right? And in a more abstract way, you can think about it this way. So in the stimulus space, which is much more than 3 dimensions, of course, each natural image is a point, and basically the way to increase would be to just go always in the same direction. Okay? Remember the gradient analogy? I think this is clear here. Okay. Unfortunately, what we found is that, it's much messier than that. Okay? So it seems that the local ST is depending on basically where you start from. So the question is it complete chaos or is there some order? And do we still have a chance to figure it out? So this is where we basically start about it. So first we cheated a bit and took advantage of the fact that we have this CNN model that's validated. And so we decided to just for one cell, for a single cell, we took all the images we had in the training data set and predicted the corresponding local STA. Okay? And so, basically, the immediate thing when you look at them is that they are different, but not so different, right? I mean, you see inversion of polarity, you see strange things like here, which we also see in the data. But, okay, overall, doesn't seem to change in so many directions. So we did the simplest dumb thing possible here. We tried to reduce the dimensionality of all these possible local STA. So again, for just a single cell. And so the simplest way to do dimensionality reduction, where you're not a fancy person like me, is to actually do PCA on them. And just doing simple PCA, we found that the 2 first principal components explains 80 to 90% of the variance depending on the cell. So we thought, oh, that's interesting, because now I have a subspace where I can plot all my local STA. I will preserve most of the variance of these local STA. I will lose the variance of the natural image, because of course natural images are much more than 2 dimensions. But at least I will actually just have something which is relevant for the local STA, and maybe I can start to understand what's going on there. So that's what we did. So basically the idea is that, every time you have a pair between the reference image here and the corresponding local STA, you can basically just plot it in the space defined by the 2 first principal components as a point for the natural image and an arrow for the local STA. And that arrow tells you if you want to increase the fine rate starting from that image, what you should do is to go in this direction. Okay? And you can, there was a question? And you can do that not just for one image, you can do that for other images. Okay, these actually are experimental point here. So you start from this image and you have to go in this direction. These axes actually mostly reflect the polarity of the local STA. So, off going in left and on going on the right direction. This is a bit more complicated, but anyway. So starting from this, then you get there. And since we had all these plated local STA, we can just plot all of them and see what it looks like. And it looks like this. And there's order out of chaos. In fact, it's much simpler than what we thought in the first place. So here you can see, I'm sorry, the quality of the image is a bit bizarre. Sorry, it's fine. I mean, you get the main point. That basically, all these arrows tells you where you should go to increase the fine rate. And so basically, wherever you start from, it's always telling you to get away from that point. You need to diverge. Okay? And so, what is that point? Well, that point actually corresponds to basically an image that would just be a uniform gray. So basically, what this cell is telling you is that I don't care where you are, just get away from here. So that means that if you only have, and so basically, what does that mean? So that means that basically, if you start from this image here, there's a big dark thing here, right? And so basically, if you already have some dark stuff inside your receptive center, you should get even darker, even more in that direction. Opposite, if you start with something very bright inside the receptive field, you should get even brighter. So in that direction. That's essentially, more or less, intuitively, at least when we saw that plot, when we did this visualization, this is what actually we interpreted as what the cell is asking for. And so basically it's like, dark, get darker, bright, get dark, get brighter, get away from the gray, which means basically the cell is wanting more contrast. So, and here I mean, by contrast, what I mean is basically that you take, for each pixel, the square difference between the luminance of that pixel and, let's say, an average gray, and then you do the averaging over the square difference over the receptive field center, okay? Because, there are many different versions of contrast. Yes?
Just a quick question. Do you have some global normalization, or you can also have completely black or completely white stimulus?
So here, actually, yeah, we didn't try that, because here all the images we presented have the same mean and the same variance. So, but locally things can change. Okay, so the hypothesis from there was to say, well, the response is proportional to local contrast. So we built this very simple contrast model. So as I said, you just take the square difference between each pixel and gray, and then you just average over the receptive field. It's very, very small number of parameters. And we asked if that model could reproduce the vector field, and at least quantitatively, it does a pretty good job at doing so. We actually compared this contrast model with the CNN. Interestingly, it performs well, but not as well as the CNN. So I think the CNN captures more. I mean, basically, it's a good approximation of the CNN, if you want, basically. But it's an interesting approximation because it's a very low-dimensional one. It's a very meaningful one. We understand what's going on there. But then, first we're like, okay. Yes.
Just to clarify exactly what you mean by this contrast model.
Yep.
So this just multiplies the tuning function by something that has to do with contrast, but it doesn't change its shape.
Yeah, I wish I had the mathematical formula here, but it's basically just you take every luminance here, you do the square difference. I think you got that one. Then you basically do some sort of a weighted average across the receptive field center, and you can use that plus some scaling factor. You can use that as a predictor for the response of your cell. It's very
so
dumb.
You're not modeling. You're modeling things directly into space.
You basically you can not exactly. Well here. Sorry, maybe I missed your question.
I'm just wondering if the model operates in the space of tuning functions of the cells or in the space of this projection.
No, it operates on the full image in the first place. Then you can always back project it here.
And how do you get shifts in the receptive field via this contrast model, or you don't?
You don't. Basically, So these are the details which I don't think are necessarily very smart here. We basically just got that receptive field center from the global estimation, and we just fit a Gaussian shape to it, which is a classical thing to do, at least in the retina. And then we use that Gaussian shape to give the weight that we need for every contrast for the contrast model. So basically, it's like contrast weighted by the Gaussian shape of the global receptive fields. But I don't think these details matter so much, to be honest. It's just that it's a really low number of parameters. It's very pretty much. I mean, there's very little parameter to do here. It's like at the end of the day, if you take apart the Gaussian thing, we have like 2 parameters. Anyway, I mean, the important point is I don't think this contrast model captures everything, but it does capture significantly. I mean, it does capture the meaning of all that. It does predict displacement of locality. Qualitatively, I think it's a good model. Quantitatively, it's not the perfect one. Anyway, so point is actually it does a pretty good job. And then we're like, okay, so but this actually is entirely. I mean, this is model based. Like we use the CNN to actually get this vector field. Can we go back to the data in a model-free way and see if all this is actually is actually true. And so first is actually we wonder, okay, can we find cases where there is a striking correspondence between the image and the local STEA, given what we know, given that basically dark region should give rise to off region on the local STEA, and bright region should give rise to on local STEA. So again, red is on, blue is off, and actually in some cases it's pretty striking. I mean, you see this, this very bright bar inside the receptive field, and you have this Gabor shape here. You have this very bright region. It goes this dark here, this goes here, and so forth. But this is, admittedly, this is cherry picking. Okay, so we wanted to have something. It's very nice. Shows you that you can find some sort of Gabor receptive field in the retina, so that's nice. But it's obviously very very cherry picking. So we thought about, is there something more systematic we can do? And then we thought about, okay, so one of the hypotheses we got here is that basically if you start from an image here, you should go in that direction. But now, if you actually take the negative image, and by negative I mean that everything which is black will replace it by something white, and vice versa. So in that frame, if you assume that this is perfectly the center, the perfect average gray, basically you should go in the other direction, which means that basically you should exactly invert the local STEA. Okay? So that's a test which is entirely model-free here. And I don't think it will work for every cell because sometimes the center is actually not the average gray. But okay, could work for some cells. And so that's an example where, okay, we measure the local STEA for all these cells, and you can see that these are always like 4 images, all these images, sorry, this is one cell. And you can see that these images are always the negative of this one, right? And so this is the local STEA we see for these guys, mostly off ones. And this is what it looks like when you actually go for the negative ones. So indeed, we do find that off local STEA in the images here actually turned into on for the inverted or negative counterpart. Yes?
Cells that have both contrasting, like in the slide before that.
Sorry?
The slide before that you have some cells with contrasting.
Yeah. Sometimes you see more than one subregion.
Okay.
Yeah. Like this, for example, that's what you're asking for.
Sorry.
So what's your question then? I'm not sure.
The last cell, like on the bottom.
Yeah, sorry, this one?
Yeah.
Yes.
So if you also invert or take the negative of that image,
Yeah.
you also get inverted.
Yeah, I'm not sure we've seen that in the data because there are issues with actually, we don't know where are the receptive field while we're doing the experiment. We cannot know it post-hoc, offline. So I'm not sure we have actually found an example of that which is inverting, but just because I think it's bad luck basically. You need to have exactly this being in the right place and inverting. So my guess is that maybe with actually non-natural stimuli where you really fine-tune with a grid, for example, maybe you should see it. But yeah, good question. Anyway, so that simple thing actually worked. So in conclusion here, basically, polarity here is actually depending on context. I think I spent my entire talk on that. The important thing here is that in fact I think that most of the ganglion cells receive both input from the on and the off pathway. And we kind of suspected that. What I think is interesting here is that in fact the fact that the images kind of change the respective contribution of them, right? So that's the kind of novel part there. And so it's not because you feel like it's a pure or almost pure off cell that it actually is when you actually interrogate it with natural images. And we have a model that claims this finding, and basically behind all this context dependency, there's in fact some invariance that you can see once you start to do that kind of plot, right? So now, just to kind of open, I mean, well, that's my last slide, but basically, I think this might also be a way to test model. I think I said something about this already. Like by measuring this local STEA, you kind of provide more constraint than the average response to a given image or given stimulus. I also think, like, I always hear this thing about mixed selectivity. And I think that basically, when you find mess, maybe you just have selectivity to a more abstract features. So since I've heard that word many times here, I was just wondering about that. Another thing also is that, at the end of the day, we've heard a lot about low dimensionality inference of, that kind of thing, of dynamical landscape. And I was wondering if there was a mapping between what I'm showing here and inference of population dynamics when you're trying to reconstruct the full dynamics here. But I don't know. I'm open to ideas or discussion about this. And of course, everything I've showed you so far, there's nothing that's really retinal dependent. I mean, maybe the end. But the idea of measuring localistic to somewhat uncover computations is, I think, a general idea that could be probably expanded to other sensory structure. Just to leave that in mind. And so, of course, I want to acknowledge the people who actually did the work. So in particular, Matthias Goldin, Baptiste Lefebvre, and Samuel Virginie, a postdoc and two great students in the lab. Ulysses was actually also involved in that, you probably know him. And also Thierry Morin, Nicole Normal, and Alex Secker in Göttingen University, who helped a lot for the CNN part. And if you're interested in this, or basically in the retina in general, I mean, I'm going to recruit soon because of that little thing that happened recently. So please drop me a note. Thank you for your attention.
Thank you very much for this nice talk. So we have time for a couple of questions.
Yep.
Very simplistic question, but do you think there's a role for feedback in this story?
So feedback from where?
From the stuff after that treatment cells.
Like the brain?
Yeah.
No. Well, I guarantee no, because we're doing that in vitro. So it's a very simple way to answer. It's a very straightforward answer to your question.
It's good that I asked that.
Thanks for giving me the opportunity to.
But there is another variation of this question that makes more sense in English. So I was wondering, so the contrast manipulation of the fact that the contrast changes the properties of tuning function. Like you can imagine certain type of mechanisms that will do that, perhaps. But maybe the deviations, so the part of the nonlinear component, so the position specificity that is not explained by the contrast, could that component residual be explained by the activity of other neurons in the ganglion cells population?
So, well, you're getting into the mechanistic inside of all this. This is definitely something we've started to explore, and we're going to explore more. I think, one of the things we want to test also is basically to start simple in the classic, is to actually test about the role of surround. So you can do the same experiment, just like mask the surround and see if it actually impacts the locality. It's actually not only a way to figure out what's going on in this, it's also actually a way to probe the role of the surround during natural stimuli. And my take is that at least in some cases, from what I've seen in data in that experiment, sometimes you see the sometimes, not very often, but sometimes you see the locality actually going away, like beyond the receptacle center. So then I think there's something interesting to probe here, but we haven't done it yet. But that's definitely on the map. And in terms of mechanisms, sorry, it's too exciting, so I have to show it. We actually have a set of tools which I really like, where we're starting to really also do perturbation at the level of the circuit. Basically. We have basically tools where we can basically genetically express orthogenetic proteins in like specific cell type inside the retina, in the middle layers, which are the ones that are really hard to access. And then we basically can optically just perturb these guys while we are doing visual stimulation and recordings. And so we tested that this actually works, and we can see the impact of the perturbation on ganglion cells. And I'm looking forward to kind of use that kind of tool to also see who is doing what, especially during natural stimulus processing. That's the teaser. Yes?
I was wondering how the spike tuning distribution look like, because when you're taking the SK, you're taking the mean of that distribution, but how that would look like, and if it's it has more modes.
Yeah, that's a great question. So basically, as I said, you're in the neighborhood, so we're making a linear approximation.
Yeah.
But basically, you can actually try to do quadratic approximation, and so ask about basically spike trigger covariance or things like this. We haven't looked at it. One of the issues is that since the stimulus is very high dimension, this might be a bit harder to estimate. Harder does not mean impossible. Actually, this is why, that kind of thing and others are reasons why I actually was also poking Christine about, hey, actually, I like your idea of trying to estimate receptive field with not so many data, maybe there's actually something to do there, and so on and so forth. So yeah, that's a good question. I mean, I don't have the answer, but I think it will be interesting to explore. See?
I assume that there will be a lot of unknowns that when you have Gaussian noise, the things are more simple with natural stimuli.
Well, no, here we are in a white regime, because at the end of the day, basically, like, we are riding on the natural image, but then the perturbations are white.
Yeah.
So then you can actually apply all the tools. You still have the simplicity of probing things with white noise. You avoid all the issues related to the fact that you have, statistical dependency in the natural image itself.
Oh, so that does Gaussian noise the image statistics somehow?
Not exactly.
Of...
Not exactly, but if you allow me to just go back a bit. You know why then you can, I mean, sorry, to go back a lot, and then the computer doesn't like it. Point is, when you do the analysis here, you start from an image, and then you have the perturbation. But when you do this local spectral average estimation, you don't care about the image, you just look at the perturbation themselves, right? So in that very moment, everything is white and fine. Okay? But of course, that's not, yeah, I mean, this was at the beginning, it doesn't matter. But of course, I mean, that's only because basically you are at a certain point and you don't care about exactly what that point is. You just move around in a symmetrical manner, so then you're fine. That makes everything simpler.
Okay, so let's thank our speaker. So we will now have a lunch break, finally, and we will continue at 2 p.m.
We should have closing session as planned.